Good morning, everyone. I'll be talking on overpressure evolution during Sedimentary Basin Diagenesis. This research was conducted at Department of Geological Sciences at University of Missouri under the guidance of my advisor, Dr. Martin Appold. How do I change this slide? There are numerous examples of rapid fluid migration in the sedimentary basins in the world. For example, in the South Eugene Island field in the Gulf of Mexico basin, we can observe that fluids have migrated at rates of millimeter per year to as high as hundreds of meters per year across the thick, low permeability sediments. And previous research proposed that solitary waves could be responsible for rapid fluid transport in low permeability sediments. These solitary waves, they are manifested as high porosity and high fluid pressure migrating in the low pressure gradient. And these solitary waves, they formed when the rate of fluid pressure generation is high relative to the fluid pressure diffusion. And our previous calculations showed in order to form the oil solitary waves, the pressure generation rate, the ratio of the pressure generation rate to the hydraulic diffusivity should be greater than 10 to the power 8 Pascal per meter square. And for the methane solitary waves to form and propagate, if this threshold ratio for Pg over D is valid also for methane, then higher methane diffusivity requires the higher pressure generation rate, which is nearly around 2,000 Pascal per year. So our hypothesis was fluid pressure generation rates high enough to form oil and methane solitary waves can be generated by sediment compaction and hydrocarbon formation under geologically realistic conditions. And we tested this hypothesis using the Basin Mode software, Basin Mode 2D software, which calculated the two-dimensional modeling of sediment compaction and fluid pressure evolution across the 5-kilometer deep sedimentary basin. And our research question was, what is the maximum possible pressure generation rate from sediment compaction and hydrocarbon formation in a sedimentary basin? We tested this hypothesis using 3 scenarios. First one as the base case scenario, where basin properties resemble the properties from Eugene Island 330 mini basin. And the second one, high pressure rate scenario, where basin properties we use that basin properties so as to maximize the pressure generation. And the third scenario was the low pressure rate scenario, basin properties used to minimize the pressure generation. And these are the model parameter values that we use for 3 different scenarios, for base case, low pressure rate, and the high pressure rate scenarios. And this is the stratigraphic evolution of the basin. So before 3.1 million years, sedimentation started in the basin with the hydrocarbon source rock emplaced at the bottom of the basin, and the simulation was run over time, and this is the present day cross-section for this basin. And once the source rock was buried deeper enough to form the oil and gas, hydrocarbons were formed, and this is the plot showing the saturation of oil and gas as a function of time. So what we see here is after 1.5 million years, oil starts to form and then reach a peak saturation at 1.02 million years, and then after that it declines to the 0 level, and then after oil, gas starts to form, and then it increases to the present time. And the lower plots, 2 plots, shows the oil and natural gas saturation as a function of depth and as a function of time. So what we see here is this oil and gas saturation shown within the source rock. They confined in the source rock. They didn't move to the shallow region. This is the plot for overpressure evolution in the basin. So before 3.1 million years ago, the pore pressure were nearly hydrostatic, and after that time, overpressure starts to develop in the basin, and once again, when the hydrocarbons were formed in the source rock, pore pressures were added, and there's a significant amount of overpressure in the source rock. So using the pore pressures, we calculated the pressure generation rate for the base case scenario. So here's the plot for the pore pressure as a function of time, and this is the pressure generation rate as a function of time. So for the first these curves, the green curve shows the hydrostatic, red lithostatic, and the dashed blue line indicates the compaction disequilibrium, and then the solid black line indicates the pore pressure in the source rock. So what we see here is before 1.5 million years, pore pressure was mainly from compaction disequilibrium, and once the hydrocarbon forms around 1.5 million years, the pore pressure increases compared to the compaction disequilibrium. And once it reaches the threshold pressure or the critical pressure, hydraulic fracturing occurred, and the pore pressure is released, and it drops down, declined, and then when the fracture closes, pore pressure again build up, and then the process repeats with time. And this is a plot for the pressure generation rate as a function of time. So the compaction disequilibrium pressure rate is around 20 pascal per year compared to the 50 pascal per year maximum pressure rate from the overall pressure generation rate. And we can see there are 3 peaks of pressure generation rate increase, which might be, we can form 3 multiple solitary waves. And this is the plot for high pressure rate scenario. And in the high pressure rate scenario, we can observe 2 episodes of pressure rate increase, and the rates reach maximum of 513 pascal per year. And low pressure rate scenario, since we have negligible hydrocarbon formation, and also the pore pressure diffuses back into the medium because of high hydraulic diffusivity, we have negligible pressure generation rate from the hydrocarbon formation. And this is the plot for PG/D ratio as a function of time, and for 3 different scenarios. For the base case low pressure rate scenario, this lies below the threshold value for solitary wave formation, and for the high pressure rate scenario, it intersected at around 0.07 million years. So we can say that solitary waves only form after 0.07 million years when the hydrocarbon starts to form. And this is the PG/D ratio with depth for the high pressure rate scenario for the present time. And the solitary wave threshold intersects at 4.2 kilometer depths. So this tells us solitary waves are formed beneath that depth, greater depth of 4.2 kilometer. So at shallower depths, hydraulic diffusivity is higher, so solitary waves could not form at shallow depth. Only if there exists high pressure generation rate at shallow depths, solitary waves could be able to form. So combining all results, could methane solitary waves form at sedimentary basins? It is unlikely from sediment compaction and hydrocarbon formation, since the methane waves require pressure generation rate of 2,000 pascal per year. In our case, we calculate the pressure generation rate could vary between 2 to 513 pascal per year. So it could be possible if earthquakes are increasing the pore pressures instantaneously in the sedimentary basins at rates enough to form the methane waves. So here are my conclusions. Pressure generation rate from compaction disequilibrium and hydrocarbon formation in a sedimentary basin could vary from 2 pascal per year to 513 pascal per year. Solitary waves could form and propagate at depths greater than 4.2 kilometer as a result of the compaction disequilibrium and hydrocarbon formation. Methane waves could form in sedimentary basin if there exists more rapid full pressure generating mechanisms. And earthquakes may also allow solitary waves to form at shallower depths. in sedimentary basins. Thank you.